I would like to thank the organizers for this truly wonderful conference. I've been enjoying it very much, and the talks are very interesting. Thank you. So I'm going to talk about how in a conformally invariant action, you can still create a magnetic monopole through quantum corrections, even though you don't have a mass term in the Lagrangian. Okay. First, I'm just going to mention just some basic things here that I think many of you would know. So symmetry itself, so why do you want to put symmetry in physics? First, I think there's an aesthetic appeal, but of course, it's also very useful. So it guides us in constructing our models. And of course, Lorentz and gauge invariants are at the heart of the standard model. The other thing that was a very important development was this spontaneous symmetry breaking. And the reason that's important is that you're not breaking the symmetry of the Lagrangian. It's just the vacuum doesn't share the symmetry of the Lagrangian. So you don't destroy renormalizability. All right. So that was a huge development. And it's a beautiful, also just a very beautiful idea. So if you broke the symmetry by hand, a lot of times you would not be able to renormalize your theories. That would certainly be true of like the vector gauge bosons. If you gave them explicitly mass, then the theory would not be renormalizable. Okay, what's not so well known as a symmetry or not talked as much about is scale symmetry. However, it's kind of interesting that the classical action of the standard model is already globally scale invariant, okay, except for the Higgs mass term, right? So the Higgs mass term does break scale symmetry, but without that, the rest is actually scale invariant. Also, what's really interesting in this regard is the role that gravity plays. So if you want to create a Weyl invariant, if you want to think of that as a kind of a related scale invariance, containing a scalar, you actually need to include this 1/6 R phi squared term that I'm sure many of you have seen before. So gravity plays an important role in maintaining this scale invariance. So now, if you have a conformally invariant action and you don't have a mass term, well, how are you going to create the spontaneous symmetry breaking? Well, there was a mechanism quite a while ago by Coleman and Weinberg, and it's that through quantum corrections, you change the potential to a point that you now get spontaneous symmetry breaking. And it's called radiatively induced spontaneous symmetry breaking. And a good example where this was used is a paper by Christopher T. Hill at Fermilab. Is the Higgs boson associated with Coleman-Weinberg dynamical symmetry breaking? And what they do is they start with a classical scale invariant action. So they have the Higgs term, but no mass. And then they generate a mass through these quantum corrections. It does not seem like it can predict the mass of the boson, but it would give it some mass. So that's how this idea has been used in the past. Okay, I don't know if you could see my screen on top there. So the question is, how does one introduce a length scale in a conformally invariant theory? So one way is to add quantum corrections. And this breaks the scale symmetry because you introduce a renormalization scale M, all right? So that's one way to break the quantum correction. And in a conformally invariant action, you're not gonna have a mass term, so how do you generate the spontaneous symmetry breaking? Well, it is radiatively induced after quantum corrections. So as I mentioned, it's the Coleman-Weinberg mechanism, and it involves trading a dimensionless parameter for a dimensionful parameter, and that's called dimensional transmutation. So the VEV is obtained from the effective potential after one loop quantum corrections. So the original potential wouldn't have it, but after the... So what we're going to do is we're going to apply this to a magnetic monopole, which does require spontaneous symmetry breaking, and in a theory which is conformally coupled to gravity. So this work was already done in one sense classically by Manu Paranjapi and collaborators, and I'll show you sort of the idea there. Sorry, can you see the top of the screen, the title?
Yes.
Yes.
Oh, okay, just I can't see it on mine. Okay, okay, that's good. All right. So this is the action. Okay, for you cannot have an Einstein-Hilbert term because that's not invariant under conformal transformations. So you have an abelian, non-abelian Higgs, non-abelian term here, non-abelian gauge fields. You have the covariant derivative, you have your 1/6 r phi squared, but you have a triplet of scalar field because that's what you need to get your magnetic monopole. But you could think of it as r phi squared, and this is lambda phi 4. So the crucial point here is this. To have this being classically sort of scale invariant, or what we call Weyl invariant, okay, with gravity, you cannot have a mass term mu squared phi squared. But, okay, the nice thing is you can have a term 1/6 r phi squared, okay? So you kind of are replacing that, and that does not break the this wonderful symmetry that you have here. So I'll tell you what previous work did is they realized that with this action, if you state by hand that your background is ADS, okay, here our R is positive in our convention, okay? So you would get a VEV, a non-zero VEV, which would just be based on the Ricci scalar of in ADS space, okay? Which would be if you think of a cosmological constant, would be like 4 lambda. So you can create via gravitation, okay, a VEV. All right. So this is like all classical. What we're doing is like the quantum version, and we're not putting the R by hand. What the R at ADS, what we're going to do is we're going to get a VEV, and the R, the Ricci scalar, is going to be given in terms of this VEV, in terms of this thing, and that's going to be generated quantum mechanically, okay? And we'll get a scale that way too. So you have a divergent finite part of the effective action. I think many of you who have worked in this area will know that the one loop divergent action is given in terms of the trace, and A2x is called the Schwinger-DeWitt coefficient. And so you get this thing called the trace anomaly. So quantum corrections actually lead to a non-zero trace. And this quantity A2x is well known. It's being calculated often. For those of you who know a little bit of the technical part here, it's 11/3 and not 3 here with the lambda squared over 4. And that's because you have a triplet of scalar fields instead of a single scalar field. And you also have this composite operator. Now we're working in ADS space, which has a symmetry, SO23 symmetry. And that symmetry, the only rank 2 tensor that obeys that symmetry is G mu nu. So the expectation value of T mu nu in this ADS space can be expressed in this way, because it has to be proportional to G mu nu, okay? And that's because of the symmetries of the ADS space. So we know the trace, and so we can figure this out. Now we're going to look at the Feynman diagrams for, it's just I can't see the top of my screen. I'm going to see if I could lower the screen a bit. It's okay. I should know it by heart. Okay, so these are Feynman diagrams for a triplet of scalar fields. And your potential now is lambda phi 4, okay, which I think many of you know, and then this r phi squared term, okay? So there are two vertices which can be combined into a single vertex, okay? And this is to get the effective potential, okay? And it's basically the double derivative of u, okay? So you get a vertex minus r over 3, you get the lambda phi squared over 2, okay, with two things, and you can combine that as one vertex, and that's just the double derivative of the third. Now, why are we looking at the third component? Because we're going to put the VEV, okay, in the third component of the scalar field. The scalar field has 3 components, but we can just make the VEV go into the third component. So what do the Feynman diagrams look like? You have the one at the top, which is the loops of theta 3, okay? But you also have loops with phi 2 and phi 1, okay? Phi 2, phi 1, phi 3. And so this one, the next two ones here, these Feynman diagrams, those can be obtained from the previous one, the first one, by simply making lambda go to lambda over 3. And the reason for this is simply that when you have this term here, you take double derivative with respect to phi 1, okay? And in the lambda phi 4, what you have is 2 theta 1 squared, theta 3 squared. And so you take derivatives of theta 1, all the theta 1s are gone, and you're left with theta 3, all right? So the expectation value of phi 1 and phi 2 are 0, okay? But they still contribute to the effective potential, all right? And the classical field is called the expectation value of theta. So the effective potential, the way you calculate it is simply you add up all these vertices, and that's the n equals 1 to infinity, and you just add up all the propagators. And the propagators are massless. We don't have a mu squared phi squared term here. And the part at the top is this u double prime theta, u double prime phi, okay? And to the power of n. So this is the calculation one has to do. These are common calculations, but people have done them. Except the problem is that the cutoff, lambda, it becomes cutoff dependent and also divergent as the cutoff goes to infinity. The potential is this potential that I just calculated here, but that's only for the first set of Feynman diagrams, but there's the 2 next sets of Feynman diagrams that you have to add. Okay, and that's V, and then so you add up 2V with lambda going to lambda over 2. So it's divergent. How do you deal with this? Well, it's counter terms. So this is quite standard, okay? All you do now is add 2 counter terms, and you get A and B such that you get your renormalized conditions. And the renormalized conditions is lambda is defined as 4 derivatives, okay, evaluated at the renormalization scale m, and then minus r over 3 taking as 2 derivatives of the potential. So basically lambda is a running coupling constant. It depends on the renormalization scale. Once you do that, the cutoff goes away and everything is nice and finite. But the crucial point is you get these logarithmic terms in the potential. So this is the potential we start off with, okay? But the loop corrections give us this logarithmic. And this is kind of well known, okay, that you get these logarithmic terms, okay? So now we can find the minimum of the potential. That will be our VEV. And we're free to just fix the VEV to be at the renormalization scale n. Okay. So now we take the derivative of the potential with respect to the field and we make it to 0. And that gives us our VEV, okay? And when you do that, lambda is no longer a free parameter. What we stick in here is our ADS is this, and you get that from the gravity field equations. Okay, this square root of 10 lambda v squared. And then when you make that equal to 0, lambda is no longer a free parameter. So the dimensionless lambda is traded for the dimensional VEV, okay? And that's what we call dimensional transmutation. So the basic idea is after the quantum corrections, now you're gonna have this VEV, and the VEV sets the Ricci scalar and also sets the value of the vector. So the crucial, I mean, all of this is really getting this nice potential logarithmic corrections. Then there's the operator, composite operator E, and this can be obtained from the one loop part of the effective potential. The one loop part is the part with those logarithmic terms here. Okay. And you can just calculate it. All right, and this appears in the quantum corrected field equations for the scalar field equation. All right, it's a bit messy, but it's calculable. All right, so now we want to get our magnetic monopole. Okay, so now we're in our ADS, everything is nice. We have our VEV, so we've broken the symmetry, and everything can proceed as before to get your magnetic monopole. So in essence, everything that continues now is something that would proceed in any calculation of the magnetic monopole. And the magnetic monopole is calculated in spherical symmetry, okay? So you have a spherically symmetric metric, and that requires only two functions of R. Then our scalar field is spherically symmetric, so it's f of r with this dependence on angles. And the gauge fields, the non-abelian gauge fields are, how do you call it, are proportional to the killing vectors of SO3, okay? And that's how you maintain the spherical symmetry. And then you use, so you basically have n of r, psi of r, f of r, and little a of r, and you get the equations of motion for each one. Okay, so that's
okay.
how you work it.
Ariel,
Sorry?
2 minutes.
2 minutes? Good,
yes.
Because the rest is just, I think I could go pretty fast for the rest. Okay, thank you. So these are the equations of motion. Okay, bang, bang, bang. Okay, and now the crucial part is that we can get the Ricci scalar by looking at the asymptotic part of the gravity equation and the scalar equations. The EO can be substituted for this. So in here, we put it in there, and we get, where the Ricci scalar is 12K, K, we get an equation for it. So we're able to get from the equations of motion what the R actually is in terms of the VEV, which you cannot get classically, all right? So you generate this VEV, and the Ricci scalar of ADS spacetime is given in terms of this. And then you can just solve the equations of motion. So this is a nice magnetic monopole there with F, and that's the gauge field over there. Okay, so for future work, we can look at gauge field fluctuations, because we've only looked at scalar field fluctuations here. And one possibility is, could the quantum corrected effective potential lead a solution in this Sitter space, which I do not know the answer to that. Thank you.
Okay, thank you very much.
Yep.
Questions, Gerardo?
Hi, thank you for the talk. Could you comment
Yes.
on what would be, how can this be seen from the dual CFT to this ADS spacetime?
I don't know too much about ADS CFT, but basically it may correspond, this ADS space may correspond to some conformal field theory in one less dimension. What that conformal field theory would be, I don't really know. When we did this work, there was somebody at McGill who wanted to work on that with me. So I actually don't know the answer to that.
Okay, great. And what would you think would be the result in higher dimensions?
Higher dimensions.
Because that would change.
I don't. Yeah. Higher dimensions. Well, I think first of all, the gravity part here, Weyl squared. I think that's in 4 dimensions that it's conformally invariant. And also this this non-abelian part may also just work in 4 dimensions. So I don't know if it's that easy to make it in higher dimensions.
Okay, thank you very much.
Yes.